Welcome. In this video, we're going to be looking at inverse relations and understanding what an inverse is and how to find it, whether we're given a table or a function. First, let's understand what an inverse function is, and you'll see that at the top of your notes. But it's simply just any set of ordered pairs, x and y, where the roles of the independent variable and the dependent variable are reversed. And you're going to see how that works when we look at some of these different examples. Let's start by looking at a table. So here we have our first table. That represents a relation. What's a relation? A relation is just simply any set of ordered pairs. Now, to be a function, what it means is that relation needs to have for every input, we need to have exactly one output. Meaning for each individual x, we can have only one unique y. So here we have -2 for x and 1 for y, or -1 for x, 4 for y, and so on. So we can see that we have 4 different individual variable values for x, and each of them have their own unique value for y. It's kind of like if you walk up to a snack machine and you put in a code like D2 and you get M&Ms out. If someone else were to come up and also put D2, they would also expect to get M&Ms. But if you typed in D2 and got M&Ms and the person behind you typed in D2 and got a bag of licorice, well, that's not a function because you have you have an input with 2 different outputs. So the inverse, just simply, if you look at these 2 tables, the inverse simply takes and switches the domain and range. So what was our x's, if you notice, are now our y's. And our y values are now our x's. They switched places. Now let's look at this inverse. Is this inverse a function? Well, in your notes, they took and reordered the table. Now you don't necessarily have to do that. Sometimes you can just do it by looking. And one thing that I see right off the bat is that I have this value for 1 as an output of -2. And this value of 1 has a different output of 1. So right away that tells me that this is not a function. Where the original one, that was a function. So I want you guys to take what we just talked about, and I want you to look at this table of values that you have in your notes, and I want you to find the inverse. So basically just switch the x and y. It's literally that simple. And then I want you to figure out, is the inverse also a function? So go ahead and pause this video and hit play when you're ready to check to see if you got it correct. So when you switch these values for the x and the y, when you swap those 2 rows, you should have this new table as your answer. And then the question is this new relation a function? So is the inverse a function? And yes, it is, because you notice each value for x has its own unique value for y. It has its own output. So that's the most basic way that we can look at these, is just, if we have a table of values, we can just swap the x and y's. Now, when we look at a function like this, and we want to find the inverse for that function, we just have to do a few easy steps. Now, if it's already written in the form y equals x squared, we don't have to do the first step. But if it is written as a function, like this one is, we're just going to change a f of x to a y. So I'm just going to look at this as being y equals x squared, which I believe is what you have in your notes. Now, we're going to go to the next step. The next step is we're going to switch the roles of the x and y. So literally what that means is I'm going to switch the y to an x and switch the x to a y. So we switch their roles. And now our goal is to solve for y. Now remember, in this chapter we've learned if we want to get the y squared by itself, or the y by itself, we would simply undo the power by using a root. So I'm going to take the square root of both sides. Now the problem when we take the square root of both sides, we're going to have 2 solutions. So technically we get y equals plus or minus square root of x. You might be wondering, why is it that we have 2 solutions? Well, let's look at it in a less abstract way. If we're trying to figure out this, if I want to figure out what 2 numbers I would square to get 9, we would say, well, I could square 3 or I could square -3. And the way that we would get that is if I took the square root of both sides, I'd have to say that we're going to have 2 solutions, a plus and a minus, and the square root of 9 would be 3, so that's how we would get 3 and -3. So that's why we have 2 solutions here, a positive and a negative square root. So anytime we take the square root of both sides, remember, we're always going to have 2 solutions, a plus and a minus. Now in your notes, you guys have what the graph of y equals x squared looks like. And the equation for the inverse we just found here, y equals plus or minus square root of x. So in blue is the equation or the graph for y equals x squared. And in red, you can see what its inverse looks like, y equals plus or minus square root of x. Now that line y equals x, the green line here, that's helping us see that the inverse is a reflection over that line. So if we were to take and flip this line over the line y equals x, we would get that red line. So that's the relationship there. All right, so I want you to follow those easy steps. So the first step for this next example is to change this to be in the form y equals. So I want you guys to now replace the y to an x and the x to a y, then on your own solve for y. And we'll do the second part on together. So just do the first part. Part A, I want you to find an equation to represent the inverse of f. So pause the video and hit play when you're ready to check to see if you did it correctly. So when we look at the steps after changing the f of x to a y, we change the y to an x and the x to a y. Then we solve for y by subtracting 1 from both sides. So we get x minus 1 equals 2y. And then we divide by 2. Now technically you could leave it like that, but it's going to help us figure out if it's a function. If we simplify this a little bit further, so I'm going to change this to be, so x divided by 2, or 1/2 x, and then we'd have minus 1 over 2, so minus 1/2. So that would be the slope-intercept form of that equation. That's all you can think of it. Now, it's important that we show a difference. Now, if you recognize the original function here, we're calling this function f. So this is the inverse of that. So we use this -1 exponent to identify that it's the inverse. So it's always important, if we have it in function notation to begin with, to rewrite it in function notation. We identify this as the inverse of the original function by using that -1 exponent. Now, if you remember from what we know in algebra, what we did at the beginning of the year with linear equations are functions. So if you were to graph this out, it would have a y-intercept of -1/2 and a slope of 1/2, but it would just be a linear equation, and all linear equations are functions with the exception of a vertical line. But otherwise, any other line that's not straight up and down, those would be functions. So this is a function here. All right, so let's look at the back of your notes and let's look at this example. So here they give us, they want us to graph, and actually on your notes you already have it graphed out for you. So let me just sketch a graph of what this would look like. So this is a parabola. So I'm just going to get a couple of key points here just to be a little bit more accurate. Again, you guys already have this graphed out. There's y equals x squared. So we have what's called, so we have the vertical line test to see if a graph is a function. So this graph, when I look at it, it definitely passes the vertical line test. So I know for sure that this is a function. Now we have what's called the horizontal line test. And that says that if we draw a horizontal line and it passes through more than one point, then it's not then the inverse is not a function. So I know that the inverse of this is not going to be a function. Well, let's think about how we could restrict the domain so the inverse would be a function. So think of a way where we could just focus on just part of that graph where that part of the graph would pass the horizontal line test. And if you're thinking that we could have this side of the graph, you're correct. Because if I just focus on this part where this is saying that x is going to be greater than or equal to 0, or if we use interval notation, we could say from 0 to infinity. If we just focus on that part of the domain, now that passes the horizontal line test. Now, can you think of another way that we could restrict the domain? Well, if you're thinking the left side of the graph, maybe you even thought that originally, that would also be true. So both of these would be true if we say that x is less than or equal to 0, or we could say from -infinity to 0 if we use interval notation, but that also is going to pass the horizontal line test. We could either look at the right side or the left side. It doesn't matter how you restrict it. In either case, if you restrict it in that way, the inverse would be a function because it passes the horizontal line test. So let's see what we remember with transforming graphs. Where we've talked about transforming graphs, meaning that shift the graph left, right, up, or down, or we might also stretch them. In this case, we're not doing that. We're just moving it to the left 4 units. Move it to the left 4 units. The graph is going to be looking like this. We don't have to be perfect, but that's what the graph would look like. So now we want to identify an appropriate restriction of its domain for its inverse, because remember, right now this fails a horizontal line test. So we could do one of two things. We could either say that x has got to be greater than or equal to -4, or we could say x is going to be less than or equal to -4. Either one of those would be an appropriate restriction for our domain. So now let's look at, because it says graph the equation, identify an appropriate restriction of its domain for its inverse, and then now we got to find the inverse equation. Okay, so now we can't forget to do this last piece here. So let's find the inverse. So to find the inverse, I'm going to switch the x and y around. So change the y to an x and change the x to a y. All right, now to solve for y here, remember we're going to get rid of the square root. So I'm going to take the square root of both sides. And we just get square root of x on the left, and on the right side, the square root and the square, they undo each other. So that's what you'd have. And now to solve for y, I'm just going to subtract 4 from both sides. And for this, remember, anytime we have a square root, that tells me that, oh, we got to be careful here. So for this one, we would say that x has to be greater than or equal to 0, because we want to make sure that we don't take the square root of a negative number. So we're going to say that x has got to be greater than or equal to 0. So that would be our inverse with its restriction. And then our original function, x plus 4 squared, the inverse for that, we would use values for x that are greater than or equal to -4. So we can just pick one of those. I'll pick this one. All right, so let's go to the next example. So I actually want you guys to try this one on your own. There's 2 translations going on here. So figure out where that new location would be, and then do your best to try to figure out what the restriction in the domain would be. So all we care about is the x values for that. And let's just use the right side of the graph just to be consistent. So that way we don't have to wonder, do I use the right or the left? We'll just stick to the right side of the parabola. I'll make that clear when I go over this one, but why don't you guys try this one on your own, and then also make sure you find the inverse. After you graph it and find the restrictions to find the inverse, then I actually want you to find the inverse, and then we'll take it from there. So pause the video and hit play when you're ready to check to see if you've done it correctly. See how you did? So for this graph, it's going to move to the right 5 units and down 2 units. So I move my vertex to the right 5, down 2, and so that'd be the general shape of my parabola. So that just helps me see what the restriction should be for this domain. So its inverse would be a function. So again, like I was saying, we're just going to stick to the right side. And so I would say that our values for x are going to start at 5 and go infinitely to the right. So again, we look to see where that vertex is. So that vertex starts at 5, and we're just focusing on the right side. So from 5 to infinity is what the values we'd use in our domain. Then once we find the inverse, we switch the x and the y and solve it. So that's what I did over there in green. And once you get the final answer here, so by the way too, before you take the square root of both sides, you want to make sure you get the square root, or the quadratic piece, the squared piece, you want to get that by itself. So we add 2 to both sides and then take the square root. So we would get square root of x plus 2 plus 5 equals y. And then since we have a square root there, focus on what's in the radical. Whoops, didn't mean to use purple there. So focus on what's here, and that's helps us find our restrictions for our inverse. So in our inverse, we want to make sure that we use values for x that are greater than or equal to -2. So that way we're not taking the square root of a negative number. All right, let's look at these last couple of examples here. So this last one, we have this function, so let's go ahead and graph this. So this is going to move to the right 2 units, and it's being flipped. So remember, for our square root function looks like this. So it's going to move to the right 2 units, but then it's going to be flipped. So it's going to be going down. So it's going to look something like that. All we care about is just in general what it would look like. Now that passes the horizontal line test. So its inverse is a function. So we don't have to worry about restricting this. So the answer is yes. If so, we need to find the inverse. So we're going to change this to be y equals negative square root of x minus 2. Then let's change the x or y to an x and the x to a y. And now to solve this, before I get rid of the square root from both sides, I'm going to multiply both sides by a negative. So I get rid of that negative on the right. Now we can square both sides. So when I square both sides, we'd end up with, on the left side, negative x. When you square it, that's going to become a positive x squared. On the right side, that just gets rid of the radicals. We have y minus 2 on the right. So now to solve for y, I can just add 2 to both sides. So we get x squared plus 2 equals y. We're putting it back into function notation. I'd say that's the inverse of what we had originally. The inverse of f equals x squared plus 2. So that would be the inverse. There's no restrictions here right now. Well, actually, let's look at the domain and range. So remember, the domain and range switch. So if we're working with a problem and you're having a hard time figuring out what the domain and range would be, go back and look what we had originally. So the domain for this one, so the red graph, so I'm talking about this one here. So the domain, if we look at the graph, it's going to go from 2 to infinity. And the range is going from negative infinity up to 0. Well, remember, the domain and range switch for the inverse. So the inverse, we're going to worry about having a domain going from negative infinity to 0. And our range, if we wanted to know the range, would be from 2 to infinity. So the domain for this one would go from negative infinity to 0. So again, the easiest way to identify that is to look at the domain and range for the original function. And when you find the inverse, the domain and range switch. All right, so I want you guys to try this last one completely on your own. Now, I will tell you this, I don't really like the way that this is set up. So if you ever have a problem like this where we have a number in front, we can rewrite it as negative square root of x plus 1, and then just put that 2. Now, that's a positive 2. It's not a negative. The negative is for the radical. So we can put that at the end. That's another way you can write it if you wanted to. So either way, I want you to sketch that graph. So it's going to move to the left 1, up 2, but then it's also being flipped. So remember that when you go to sketch it. And then figure out is the inverse a function, and if so, find the inverse. And then to find what the domain would be, fill out that box at the bottom, and that'll help you find the domain of your inverse. So go ahead and pause the video and hit play when you're ready to check to see if you've done it correctly. What you did here, so for this first part, I recognize that it's going to move to the left 1, up 2, and like I said, it's going to be flipped vertically. So your graph moved to the left 1, up 2, but then instead of going up and to the right, we go down and to the left. So that passes a horizontal line test, so its inverse is going to be a function. So I switched my x and y, so we'd have x equals negative square root of y plus 1 plus 2. Now make sure that you do it in this order. So we first want to get the root by itself by subtracting 2 from both sides. So I'd have x minus 2 equals a negative square root of y plus 1. So to get rid of this negative, I multiply both sides by a negative. So this x became a negative x, this negative 2 became a positive 2, and now the right side is positive as well. So now we can get rid of the square root by squaring both sides. We could just leave it like this. You don't have to actually multiply it together and expand it out. If you did, great, but you don't need to. On the right side, we have y plus 1, so I subtract 1 from both sides to get my inverse function. And then to find the domain, at the very beginning, we can see that the original domain goes from negative 1 to infinity. So that's how I got that piece. And the range goes from negative infinity up to 2. Remember the domain and range switch. So my new domain is going to be what my range was for the original function, which was negative infinity to 2. So that's my domain of my inverse. And that's it. So good luck now as you work on your assignment.